The title of this presentation is actually coined as Physics and Optics of Micro and Nanoscale Patterning and its Applications. I am from this Center for Optical and Laser Engineering, one of the 7 active research centers under the Photonics Institute in Nanyang Technological University, Singapore. So I'm going to now into this presentation mode. So I'm not sure whether you can see me, but I understood that I cannot see you all. So I'll be talking to the slide. Okay. So if any interruption or something, please send me a message through this chat line. Yeah. Okay. In this Center for Optical and Laser Engineering, we have very many research programs, and my research group mainly focus on optical engineering with a specific focus on nanoscale optics, in which we are looking into micro and nanoscale patterning, and also some of the fundamental physics on laser material interactions. We also do bulk machining, and as well as macro and mesoscale manufacturing. But the topic of today's presentation is actually on the micro to nanoscale patterning, and we will be mainly focusing on this topic as far as today's presentation is concerned. The other important research area that we have been actively involved in during the last 25 years is on metrology, engineering metrology, ranging from macro to micro to nanoscale metrology. Of course, this metrology was my bread and butter and is my bread and butter to a certain extent. I did my PhD in optical metrology under the supervision of Professor Sirohi from IIT Madras. We are continuing on using the speckle techniques for various applications. And the recent one has been on surface metrology of next generation aerospace engine and aerospace panels and other artifacts. Then we have been also using this speckle metrology for NDT applications. And we have been using this concepts for biometrology, for mechanobiology and biometrology application. And the recent one is also for corrosion monitoring. There are a lot of industry fundings on this from Rolls-Royce, from Panasonic, like that, big MNCs are actually funding these projects. And the next important specific application area is on diagnostic biomedical optics and nanobio-optics. We have been actually trying to develop a single modality, dual modality, and multimodality diagnostic medical tools or devices, concepts, using fundamental optics, interferometry concepts, as well as fiber optics concepts. So we have been developing very high resolution axial as well as lateral resolution imaging systems for ocular imaging. And the recent invention actually in the commercialization pathway that is on the Gonio pen, which is actually focusing on the angle imaging for managing glaucoma. We have been also developing very high resolution imaging systems such as Bessel beam microscope, and also for breast cancer diagnosis, for colon cancer diagnosis, as well as for Alzheimer's disease, etc. If you are talking about some of the recent work on this diagnostic biomedical area, we can see that we have developed a fiber optics based, a specialty fiber optics based probe for imaging cells and organelles inside the cell, where you can individually excite the cells that you can see here. Just this is individually exciting the cells. And very high resolution imaging also of the, around to 500 nanometer down to 300 nanometer, very high resolution imaging also can be achieved with such approaches. And other important biomedical project has been on imaging around opaque obstacles for basically to help the, the surgeons while they are doing the surgery. So these are the major 3 areas that our group is actively involved in the recent past. So today's topic is mainly on micro and nanoscale, fabrications or nanoscale patterning, and let us focus on this topic. So the outline of this presentation will be, after giving a brief introduction, we discuss about some of the fundamentals of this patterning with lasers, focusing on continuous wave lasers as well as short pulse lasers, and then see what we can achieve with single point writing. Then we will enter into the interesting section on the beauty of interfering with interference. So what we can achieve with interference, optical interference, and how they can actually help us in the micro and the nanoscale patterning, where we'll be discussing about the fixed and stretchable periodic patterning, miniaturization from the semiconductor industry point of view, and also we'll be discussing about the conventional and near field optics and what we can achieve with those approaches as far as some of the industrial applications are concerned. Then we'll go into the random patterning. I should actually say that this is using a very it's actually a very significant work that we have been doing in the recent, very recent years. And I should thank Professor Vijayan sir for actually directly or indirectly dragging me into this random optics work. So we'll be discussing some of the random optics work that we have done in the recent years, okay? And then we also discuss a little bit about the biomimicry, and we'll conclude this talk. So let us just start with the very fundamentals, the various lasers used in material processing. Because when we are talking about the patterning or writing features, it is actually we are processing the material. We can actually use lasers that ranges the wavelength from UV ultraviolet to visible to infrared, near infrared, as well as far infrared wavelength lasers. But you can also get this if you are looking into the temporal mode of these such lasers. They can be in the continuous wave mode operation or pulsed mode operations. And we will know that the physics of material removal is quite different when we are talking about the continuous wave laser as against the pulsed mode of operations. Apart from that, we should be very much aware of not only the material properties, but also the optical properties of the light beam that we are actually going to employ while doing the material processing on certain materials. And those five important, of course, there are many other properties, but the five major important factors that you have to consider is one is laser beam power, the wavelength of the laser beam, the temporal mode, whether it is continuous wave or pulsed mode, the spatial mode. Generally, we prefer the Gaussian mode of operation, that is the TM00 mode. There are higher order modes in certain specific applications we can use, unless otherwise we really need it, okay? And then the focal spot size. I would like to emphasize, on the wavelength as well as this focal spot size when we are actually configuring a laser material processing system, for example. The most important thing out of all those things, I would rather say that is the wavelength of the laser beam when you're actually processing a material, because the absorptivity of the laser beam energy by the material depending on the wavelength of the laser radiation and the spectral absorptivity characteristics of the material that we are going to process. So wavelength of the laser beam plays a very, very important role here. The other one is actually the focal spot size. Let us just look into the wavelength of the laser beam. There are very many laser material processing, starting from the conventional single point writing to the latest advanced 3D printing approach, which you can see here. This is from a recent a multi-material 3D printer that we have developed. And you can see that, for processing different material, we are supposed to use different wavelength of the laser beam to get the best desired output. Also, you can see that if you're looking for processing other materials apart from what is listed here, such as PDMS, PI, or graphene oxides, such films, if you're trying to process and pattern features at the micro or nanoscale, you can see that the correct wavelength, the optimized wavelength that you can use actually varies from the material to material. So this is a very important consideration that we have to consider when we are using such approaches. The other important approach is actually the focal spot size. Whenever we are trying to process the material, we most of the time we try to use a lens to get the desired focal spot size. But we need to have the understanding that the focal spot size that is at this focal plane of the lens is directly proportional to the not only to the wavelength of the light that you're going to used there, but also it is directly proportional to the ratio between this focal length of this lens to the unfocused beam diameter that is going to reach this lens plane. Okay, so if you're actually trying to get a very small focal spot size, it is eventually going to increase the power density. So the power density is actually power per unit area, and that actually tells you whether you are working in the desired optimal processing region. I will discuss about this at a later stage again. However, we have to be aware that when we're trying to reduce the focal spot size, we are actually playing with another factor here, which is actually this depth of focus, or otherwise we call it as the working range of when we are configuring the system there. We normally need to have a very good working range. So if you want to have a good working range, the value of B should be larger. But you see that this B is directly proportional to this wavelength of light, and directly proportional to the square of this ratio between the focal length to the unfocused beam diameter. So while we are trying to reduce this focal spot size to increase the power density, we eventually reduce this, the depth of focus. So there is always a trade-off between the spot size and working range. So in such context, depending upon the application, we need to actually optimize these two parameters, which are very, very important, which eventually tells us that the achievable focal spot size is actually, decided by such factors. Let us just see how the material is removed when we are using a continuous wave as well as short pulse lasers. We have just seen some of the important fundamental points which we will be using every now and then when we are talking. The other one is actually the continuous and long pulse lasers and ultra-short laser pulses. In ultra-short laser pulses, we'll be using excimer and femtosecond lasers. And the time scale of these pulses are actually shown here. Basically, what I would like to highlight here is how the material processing is actually occurring when you are, or happening when you are using for example, a carbon dioxide laser or a neodymium YAG laser in the continuous mode or long pulse mode, as against a short pulse lasers such as excimer lasers as well as femtosecond lasers. And you can see that when you use a continuous wave laser such as carbon dioxide lasers or neodymium YAG lasers, there is always certain side effects such as the heat affected zone, which also form this kind of noise. We normally call this as necklace or HSH, and this is actually the origin of very many crack propagations. So we need to be very careful that we are really working at the threshold optimum region. Otherwise, you are really going to make this problem much more significant and detrimental. But if you compare this against the short pulse lasers, such as excimer lasers, for example, the material removal process is slightly different. In the case of continuous wave lasers such as CO2 NDR, the material removal is from solid state to liquid state to vapor phase. There's a real phase change of material from one phase to the other phase. In the case of excimer lasers or femtosecond lasers, when you use it, the pulse actually has got enough peak fluence that it is going to break the chemical bonds by the process called ablation. So breaking these chemical bonds directly will take the material from the solid state to the vapor phase, for example. So in such cases, you can see the quality of the processed region are having very, very subdued side effects such as heat affected zone or anything. So it is much more preferred in very many feature fabrications, whether it is in the macro scale to micro scale to nanoscale as well, depending on the applications. So these are some of the fundamentals I would like to highlight here. And let us see that in the case of short pulse lasers such as excimer lasers, which are some of the lasers either in the 365 I line or in the 166 nanometer line or 293 nanometer line, which are in the UV region, when they're using in the semiconductor industry for optical lithography, for example, they normally use a mask such as this. And we have to see that the material removal process here, as I told, is just the breaking the chemical bonds. And you can actually, when the laser beam actually passes through the mask, depending upon the openings here, you are going to actually pattern the features as per the the dimension that you are actually set here. But if you want to actually further reduce the dimension, you are normally you put a lens here. and which again follow the same equations which you have seen earlier. However, the energy density that is going to be here is very much depending on the old lens maker's formula, which we have studied in our school days. That is 1 by U plus 1 by V is equal to 1 by F. Because this is actually going to determine the energy density that is going to be here at this plane, where the laser is actually impinged the material. Why this is so significant is that you can see that if you are beyond the optimal processing region, you are going to burn the material, or you are going to actually pattern with a lot of scattering damage, or you are even going to achieve no patterning at all. So you are supposed to actually work the optimal processing region. You have to do a theoretical simulation as well as then some experimental validation before you really configure all the material, this optical parameters. Now, if you do that, you are going to see that this energy density that is at this plane is directly proportional to this a square of this demagnification factor, where the magnification we know as per the old lens maker's formula, we know that it is actually U by V. So magnification is V by U. So the demagnification is actually U by V. So this is actually going to play a very big role in the energy density of the laser beam that is going to reach at the workpiece. So this is another important consideration we have to consider. Considering all these things, let us take an example of a very ultra short laser pulse lasers. One example I want to show here is some of the work that we have been doing here. So we have been using a multi-wavelength femtosecond laser for printing very many different type features on different substrates. And this is, I'll take one example. We want to actually pattern a Fresnel zone plate of different dimensions and different zone height. And you can see that the most important thing we have to consider here is actually what is the focal spot size that we are trying to achieve here. As you know, we know that the equation that we have to follow as far as the smallest focal spot size is concerned, and which is actually going to be in the range of about 1 micron to 10 micron. And you have to remember, I forgot to tell about this point, that whenever you are using this kind of a configuration with the lens, you are always the minimum achievable spot size is always decided by the diffraction limit as well. So when you are actually using such system, you are actually doing a single point writing. Remember, a single point writing, and you can actually do the scanning, and you can get make the desired dimension, desired shape, desired feature that you are going to print or pattern on the substrate. And the substrate has to be photosensitive to the incoming wavelength of radiation, okay? And this is a very good example of this Fresnel zone plate we have made using this kind of system. And you can see that when we are doing that, we were able to make such Fresnel zone plate on flexible substrate, which can be even fixed onto the normal lens. Many of our lenses are actually based on refractive optics, and this kind of Fresnel zone plates are actually diffractive. So diffractive refractive optics combinations, which are very essential for very many optical applications, can be also made like this, which are very very small in size, of the order of micron, as I mentioned earlier. And this is a very, very simple process if you configure the system properly. This is on a polyimide sheet. We are trying to make some other patterns for sensing applications. You can see that it's so well controlled, well defined. But make sure that the dimension of the feature that we are going to pattern here inside these features are the minimum spot size. The minimum dimensions are actually of the order of micrometer range, not of the order of nanoscale range. And this is one point I would like to highlight here. So you can actually make this kind of a layer by layer fabrication, and you can stack them together, and you can get high aspect ratio 3D stacked features as well. So this kind of features are used for very many industry applications, but we have to make sure that we are working in the optimal region. And also we have to know that whether we are in the ablation region or whether in the thermal photoreduction region, because some of these patterns are actually made based on thermal photoreduction. Some of the patterns are actually made based on the ablation thing. So we have to actually fix the threshold fluence or energy density that is required here. And that is one important point we need to consider here. we can actually make very many features. As this is not the topic of our discussion here, but I just want to highlight that the features which you have just seen, that is patterned with such femtosecond lasers, are used for wearable electronics applications. We have made flexible wearable supercapacitors, flexible micro heaters, which can be even, even actually paste and as a usable, reusable attachments on very many surfaces, and also wearable sensors by making 3D porous graphene flakes using femtosecond lasers. So such things can be used with the single point writing. That's what I'm saying, single point writing and scanning option. And scanning option using different scanning methodologies, either using a AO modulators or by an F theta lens based approach that you have seen here. So this is not our main focus of our discussion today, but for students, if they're really interested, I recommend you to read this. And if you have any doubt or you want to have any interaction on this topics, you are always welcome to drop me a mail or call me. Okay. It's a very latest work that we are doing here. Okay. Now, what we are trying to achieve here is to process this kind of material, but at the same time, we are trying to achieve micro and sub-micro to nanoscale features. How can we achieve that? Here I have shown few recent publications here where we use 2 femtosecond laser beam to make volume holographic gratings. I will explain about that at a later stage. And this is the kind of gratings we have made on a substrate which are stretchable. So when you actually do a stretching, you can actually tune it. Tune what? Tune the properties by which you can use it for steering applications, beam steering application. You can also use it for spectroscopic applications. We'll be discussing about that. The other one is actually using random optics. We actually used random optics concepts. I got a very good research fellow. I recently, I get a lot of students from Professor Vijayan sir's lab, and this is one of the work done by one such research fellow who joined me, and his name is Jaya Bingi, and he was actually making random optic structures on silicon surfaces, and we have been using dark and bright silicon surfaces for various applications, including solar cell applications. Some of the things I will be showing today. And the other one is we are mimicking the nature, the surfaces that we can find in the nature, such as the desert beetle skins or butterfly wings, such as, surfaces, using the same approach of what we have adopted here with a slight variation in the concept that we adopted for writing features. Let us go through this. And those features I'm going to classify into 3. One of the feature is actually fixed periodic features. The other one is actually tunable periodic features, and the last one is random periodic features. Let us actually go through these fixed periodic features, and all these features we have fabricated using interferometry concepts. We have did patterning for 1D, 2D, and 3D features at the micro and nanoscale. So from now onwards, I'm not going to do single point writing. Rather, I'm going to large area patterning using interferometry concepts. Let us see the challenges we faced and how we can actually, we are able to subdue those challenges using optical physics, optics concepts. And that is what we are going to discuss here from a bird's eye view point of view, okay? And I would like to actually tell that some of these features that we have discussed, that we are going to discuss, we have even used to write features on graphene or FLGs, fuel layer graphenes, which were used for developing a plasmonic multi-level optical switch, which just published very recently, 2 weeks ago. However, I didn't include that topic here due to the benefit of the time limit that we have to consider. Let us go through this fabrication aspect, the feature fabrication aspect, and how we can achieve that. So whenever we talk about the interferometric based any concepts, the first formulation that comes to our mind is I is equal to I1 plus I2 plus 2 into square root of I1, I2 cosine of delta phi, where I1 and I2 are the intensities of the 2 interfering beams, and delta phi is actually the the major factor that is playing here, which we normally call the cos delta phi, we normally call as the modulation term, where delta phi is the phase difference between the two interfering arms of the interferometers. Okay, and normally to get very good contrast, which we need for most of this writing of features, we try to make sure that the two intensities are equal. So this I1 is going to be I1 plus 2 into square root of I1 like that. Okay. Now, I just use this peacock here with a specific reason, but we are not going to discuss this. Peacock is a very beautiful bird. It's of course the national bird of India. But the basic reason I have put here is that we have been using this peacock feather to study a lot of interference, concept, a lot of optical concepts such as interference, diffractions, photonic crystal, what not actually even nanoscale patterning, supercontinuum generation as well. So since that is why I use this. But the principle of fringe formation, that is actually when a peacock actually dance, is the same as the principle when we use in some of the interference approaches that we see in nature, such as soap bubble formation or thin film interference like that. So that is why I use this thing, this particular picture here. But I would like to actually emphasize that what we are more interested here is actually this delta phi term, and this is actually going to enable or restrict or enable us to define and decide the configuration that we are supposed to configure for various feature patterning. And let us go through this. This delta phi is also a very important term, because this delta phi is directly proportional to the optical path length difference between the interfering beams. It means that if you want to actually make some value to that cos delta phi term, you have to actually give some values to this optical path length difference. So these factors are very important while you configure the interferometric systems. So that is why it is important as well. So the interferometers that we are going to deal here can be broadly classified as the specular interference as well as speckle pattern-based interference. So in the specular interference, normally you can again classify this as wavefront splitting based interferometers and amplitude splitting based interferometers. All these terms are very, very basic terms. I'm sure that the students are able to understand, immediately correlate to the Michelson interferometer, Maxent interferometer, etc. that you have studied, the Young's double slit interferometer that you have studied, etc. And needless to say, that is the same interferometric concepts we are going to use this advanced way of writing these nanoscale features, which we are going to see. The one on the right hand side is actually the random patterns that you can see when a coherent light beam actually reflects from a diffusively scattering surface. And luckily I don't have to tell a lot about this, because I have seen that my advisor, my guru, Professor R.S. Sidhu, he has actually given a detailed account of a very excellent talk on this speckle metrology. So we will be using this same concepts for generating speckles. But once we generate the speckle, what we are going to do next is actually the topic of today's discussion. So these are the two things we are going to discuss from now onwards. So I would like to actually give a motivation fact. The motivation with which we have actually started doing this project for about 2-3 minutes. Basically, we started this project when we have been approached by an MNC to whether we can actually develop a system for this semiconductor fabrication using near UV or visible wavelength for writing features which can actually make the then forecasted technology nodes of sub 30 nanometers. And we have been actually trying to understand what actually the problem lying there. Of course, whenever we discuss this kind of topic, I always feel that it is not prudent to talk about this without showing these two the pictures of two great legendary scientists. This is I don't have to name, but still Sir Richard Feynman in 1959, Professor, that there is plenty of room at the bottom. And it took about 6 years when Sir Gordon Moore actually challenged the technologists to see that whether you can increase the transistor density by reducing the feature size. And that is exactly the line of work that we have been doing from on this project, and that is what we are going to see in this presentation from now onwards. I hope that many of us, of our age, and also my elders, very much know that in our time we will be using this 386 and 486 computers. I was in IIT Madras, and I was very lucky that the lab was very well equipped. And at that time, we were having this kind of, the computers. Prior to that, it was the PDP-11, the old computers. And you can see that the technology is advancing. The IC chips, the features inside are actually reducing. And you are actually now in a pocket-sized, computers, PAM tops, laptops, and also this latest one, which is flexible. Due to time limit, I am not running the video because we will move away from the main topic. So this is a flexible, the surface or a screen where you can do all kind of the computing and display applications. But basically, this has actually taken to this technologist to this problem. What is the problem? The problem is actually the critical dimension, or otherwise defined as resolution, or the feature size in the industrial technology roadmap for semiconductor is actually forecasted to be around sub 10 nanometer by 2022. We are already in 2020. This is actually a roadmap which was released a few years ago. The latest one I didn't show here, but that actually shows around 5 nanometers, okay, and below. So, but I would like to stick to this itself because this is where from where we started this research problem, okay. Now, at that time, it was actually 65 nanometer pitch size for whether you are actually taking this, DRAM or even the contact in resist. It is supposed to be the critical dimension or half pitch resolution is supposed to be around 35 nanometer. By 2016, it was 25 nanometers. Like that, it was reducing. So there is a shrinkage of the integrated circuit device dimension, which actually put a lot of stress on the scientists, the technologists who uses such technologies, and optical projection lithography is one such method. And we have seen this configuration earlier. I was showing you that using excimer lasers, if you put a mask here, you can actually get the the pattern here. But if you're talking about the feature dimension here, you can see that in the semiconductor roadmap, they were talking about a resolution. That resolution is this critical dimension. And you can see that this critical dimension is directly proportional to a process-related factor, which is normally 0.3, 0.25, like that, depending upon the process that you are using here. And it is directly proportional to the wavelength of light source and inversely proportional to the numerical aperture. And what it actually tells us is that if we want to reduce this critical dimension, which is actually our target, of course, we have to either reduce the wavelength of light source, or we have to increase the numerical aperture, which we all of us know that numerical aperture is actually, the refractive index multiplied by the sine of the angle subtended here as shown in the figure. Now, what it actually tells is that if you want to reduce this, we have to reduce the wavelength. But the problem we are going to face is already most of this dimension which they are showing in this ITRS roadmap is actually using 193 nanometer, which is already very, very short or extreme UV we are reaching. But the problem is that if you further reduce it, you cannot use any more refractive optics. You have to use new materials. There are a lot of research going on there. So the lack of suitable optics and lack of suitable photosensitive material such as photoresist is going to play very important role there. So the next question comes is that, okay, can you increase this numerical aperture? Then also you can reduce this. So if you want to actually increase this number, either you have to increase this, the refractive index, or you have to actually play with this sine theta. But there is a limit that you can play with the sine theta. The only option is to increase the numerical aperture. So what people has normally done is to increase this resolution, and it's widely known as RET, which is called resolution enhancement technique. They try to manipulate the refractive index of the medium in between. What they did is they used some high index fluid, and such high index fluid, when they use between this lens and this medium, the substrate, it is actually later known as immersion patterning or immersion lithography. But the problem is that the industry grade liquids are actually having only refractive index. The maximum achievable refractive index are about 1.65. So what to do then? Then they started using very high index glasses, such as NALF, sapphire. Even for a small glass slide, that you normally, the size of the glass slide that you use for, when you go for blood test, for example. Such a size of glass slide cost a hell lot of money. That's about a few thousand US$. So it's very expensive. But even then, you cannot actually get more than 2 refractive index. You see that? So the achievable reduction in the dimension is still limited by this. So this is the challenges faced by the engineers in the semiconductor fabs. And all this is using 193 nanometer. So the question is, what we can do at this moment. The problem given to is that can we do this with a near UV or visible wavelength? And from this context came the whole project that we have been doing over the last few years. And I would like to actually tell that we can actually do this with conventional interferometric approaches. I have actually, I was just browsing through some of the lectures of the ROWS, very excellent lectures. And I have seen a very good mentioning of this biprism based interference. And this is actually, we are starting from Young's double slit experiment, the wavefront splitting. Then the biprism based, you can also use multiprism, and or just interfere, two beam or multiple beams. Either you split the wavefront or you split the amplitude. Basically, when you split the amplitude, you mean that because square of the amplitude is intensity, so you split the intensity. Not only that, most of our light beam has got a wavelength, intensity, phase, and polarization. And you can actually play with all these parameters, and you can actually do wonders when you're doing the patterning. And let us go through this one by one. See, the one which, when you're using this biprism, basically biprism split the beam as if there are two beams originated from the two virtual source points, the old fundamentals, right? So the superposed region will be having very nice patterns, and this bright and dark patterns will be, impinging on the substrate, and you are going to get very nice patterns like this. This is actually most eye structures we pattern for some defense applications, okay? Basically, we have to know that this pitch of this pattern, which is actually going to determine our critical dimension. Critical dimension is half pitch, okay? So that is actually directly proportional to the lambda and inversely proportional to the sine of this angle, where this alpha is the prism angle. And this you can compare with the normal two beam or multiple beam interference, where in the two beam case, it is actually, the directly proportional lambda and inversely proportional to the sine of the angle, provided you are actually having a interference on an air or a vacuum, okay? So if you are doing that, you normally get straight line patterns, which you can imprint or print on a substrate, photosensitive substrate. And then you can actually transfer into semiconductor wafer. And that is actually what we are going to do here. Let us see what happens. So when we are actually using this kind of a very simple biprism based configuration, using the normal glass prism, BK7 biprism, okay? By controlling the prism angle, we can see that we can get very nice line features. And if you actually take one line features and then you rotate this wafer and for 90 degree, and then again or certain different degrees, and you are actually going to cross these two patterns, and you will be getting pillar-like patterns or this kind of patterns. But all these patterns are very good for photonic crystal applications. You fill PDMS between the structures, you can get very nice photonic crystal. Such applications can be also used. We use it for making a polarization splitter, okay, a device based on that. Now, coming back to the feature size, you can see here that this is a single exposure technique. Then you can actually get a pitch of 3.75 micron, very close to the theoretical value that we used, with an exposure dose of 200 millijoule per square centimeter. We can also get square lattice structures, and you can see that the diameter you can reduce up to the 690 nanometer. This is the kind of features you can get. And if you increase this prism angle, you can see that the feature width can be reduced to 206 nanometer. You see this? We can actually reduce the feature size from the micron to the few hundred nanometer size, just using a prism-based, biprism-based interferometer approach. So what we have to do to achieve this targeted nodes, the feature size that we have been given, that is sub 30 nanometer. So we try to do all those things. We try to increase the prism refractory index, but all those things actually took us only around 212 nanometers. So we found that it is really challenging using such approaches. So we thought that why can't we use the other amplitude splitting based approach? The advantage of using the biprism based approach is that you can get a very large area patterning, so beautifully patterned, and it has got very many applications, but not the application that we intend to start with. So so what happened is that we developed an in-house developed kind of multiple beam interferometric lithography system, which has actually a very special custom-made 2D diffraction grating, which has got a 0th order, first order, of course, very many other orders. And most of the data that I'm going to present here is actually using the 0th order, or two first order beam, or 3 first order beams, or 4 first order beams. And you can see what we can do. We can either use normal interference, and we found that when we are using that, the penetration depth is actually affecting very badly. So we want to actually go into the evanescent wave regime. And then we started doing some evanescent wave interference, and then plasmonic interference. I will go through that one by one. So this is the system. Of course, you can use change the laser wavelength by replacing different lasers, but let me discuss this particular in this presentation using 364 nanometers. When we use two counter propagating beam, that is one beam like this and the other beam like this, we were able to actually get very nice patterns, such as shown here, with a period of 253 nanometer, and of course plus minus a few nanometer, about 5 nanometers, with a line width of about 136 nanometer and 300 nanometer approximately the height. So aspect ratio is also very important, because for the semiconductor fabs, when they give us the problem, they want actually not only line features, they also want some contact pillars also. So we're also looking into the aspect ratio, that is the height to width, okay, ratio. And we found that when we use 4 counter propagating beams, we were able to get this nice pattern. These are all images taken using atomic force microscope, and you can see that these are very, very nicely patterned features. And this has got a period of 240 plus minus 5 nanometers, with a spot size of about 125 plus minus nanometers, with a height of 300 nanometers. So these pillars are actually what we are really looking at. The line features such as grating, and the contact pillars such as this. And you can see that we are still somewhere around this 100 plus nanometer size. And we try to actually do a lot of analysis and see what we can actually do further. In between, we were trying a lot of physics optics work by changing the state of polarization. you can actually change the state of polarization between the counter propagating beams. And you see that it actually follows just exactly the theoretical simulation that you're doing there. And you can get very nice, interesting features that you can see here. But only thing is that the pitch size is around 500 nanometers when we actually manipulate this state of polarization and other parameters. But this has got very nice, very important applications in biosensing and other applications. So these are the kind of work you can do. And I didn't show you that. I will also like to emphasize that with the Professor Joby Joseph from IIT Delhi, we had done a very interesting work. We not only changed the polarization, we were changing the intensity ratio between the interfering beams as well as the phase of the beams, and we were able to fabricate or come up with features which are equivalent to the crystal lattice structures, as well as the very many different interesting structures we were able to make. So what I would like to say is that with interference-based approaches, we can definitely do such a patterning, but all these are periodic patterning, okay? All these are periodic patternings. So what we have been doing is that, we were able to get this around 100 nanometer plus minus this pattern dimension. What we need to do next, this was our question. So we thought that why can't we go to the near field? Naturally, near field, we need to be able to reduce the factor wavelength compared to the excitation wavelength. So we thought that we will try to do a little bit of study on that by using plasmonic concepts. And as there are many students here in this audience, I would like to show that whenever we are discussing plasmonics, it is better to know that the gateway of the plasmonic research, I normally say that this paper is the one, okay? Because this is by Ebbesen, that there is extraordinary optical transmission through sub-wavelength Hall arrays. I encourage you all students to read this paper. It's very, very nice paper, which will give a lot of fundamental, concepts and inputs there. So I would like to actually touch upon these plasmons. Normally, as you might have heard the talk that is given a couple of days ago, where what is actually meant by surface plasmons. Okay, I just want to reiterate that surface plasmons are collective electron oscillation propagating at the interface between a metal and a dielectric. And what we are interested here is actually we want to actually make sure that the main features of SPs are the surface plasmons are met with in our pattern making, okay? That it will be giving you a shorter wavelength compared to the excitation wavelength. And there is actually enhancement in the C-axis. Why we want enhancement in the C-axis, I will discuss later, okay? And of course, it is always bound to the surface, which is quite normal, and propagation along the surface. And by optimizing this, these factors, you can actually do a very interesting pattern dimension when you do the patterning. Okay, what you need to do is that you need to use a high index prism. This is a prism based, okay, Krishman type configuration. You have to have the normal substrate and the photosensitive medium here, and between them, you need to, if you don't put it, you can actually put it in the Evanston wave regime, but you put it in the same regime, you put a metal there, and the metal is actually going to give you the plasmons. What you are actually doing is that by counter propagating these beams, you are generating actually two surface plasmon waves, and you make them interfere. And remember, the surface plasmon wavelength is directly proportional to this this value epsilon m values of this the metal as well as this dielectric. Okay, so what you have to remember is that by controlling this, we can actually control the wavelength as well as we can actually control the pattern dimension based on this interferometric equation which is developed. And you can see that the pattern dimension that is observed is very, very interesting. We were able to achieve the minimum feature size to sub 100 nanometer, around 80 nanometers. And the exposure depth is 200 nanometers. What is the significance of that? It means that the previous case, whatever interference we are doing is actually, we were not able to get this high pattern dimension when we are using the Evanston wave patterning. But when we are using the plasmon, interference, we were able to not only get the smaller feature size, but also we were able to achieve high aspect ratio. And that is what is shown here, that you can get about the line width of, if it is 2 beams, you are going to get a straight line patterns of about 90 nanometers. Or if you're using 4 beams, you are able to get about the same amount, 80 to 90 nanometer, the feature size for the contact pillars. This is the top view, and about height about 200 nanometers. So you see that if you do a comparison, if you use the conventional laser interference lithography, you are able to get a feature size of about the resolution of about 128, 130 nanometer with a aspect ratio of 2.3. And when you are actually use this near field concepts, whether it is in the Evanston wave regime to the surface plasmon regime, you are able to get not only the feature size reduced to 80 plus nanometer, we are also able to get the aspect ratio close to this value, that is about 2.3. But again, we are not near the value that we are supposed to achieve, and that is actually the feature size is less than 30 nanometer and aspect ratio is about approximately about 8 using a near UV light source. We were using actually 364 nanometer. Okay, let us see what we can do. So here comes a lot of discussions and debate how we can actually go further down the scale. Accidentally, we come across a very good paper, which I will show you after this slide. I would like to actually tell that when you have a kind of nano-sized spherical metallic objects, you can actually have stationary oscillation of this quantized electron, okay, around it, and that is normally known as localized surface plasmon. And if it is on the surface, as I mentioned earlier, you normally call it as surface plasmon polaritons. You have heard about this a couple of days ago also. Now, what we are going to do is, this is actually the work of Kawata, okay? In 2001 to 2003, he has done a lot of interesting work. So what you need to do is that you get this nano spheres, nanoparticle close to this metal surface. And if you can actually manipulate this, if R is the radius of this nanosphere, and D is the distance between the metallic surface and this sphere, and if the ratio is D by R, if you can control this D by R less than equal to 1, it's a lot of theory there. I'm sorry. What you can get is that you are able to observe a very interesting, modes, which are called electromagnetic normal modes. This is known as gap modes. So we thought that why can't we actually look into this? This is actually the a simulation that is done. You can see that when the D by R ratio is this is the without the surface, you can see that what is the emission that is shown here. Okay, but when the D by R ratio is less than 1, that is when the diameter is actually 3 nanometer, the distance between this and the other one is 10 nanometer. You can see that this is 3 nanometer and this is 5 nanometer, and you can see that the D by R ratio is less than 1. Can you see a small, enhancement here? And this is actually that normal mode, and that is called gap modes. But if the D by R ratio is actually, if this is going to be, R is going to be 10 and this is going to be 10, then you are not going to observe it again. Only between these two you are going to observe. And if you can take those modes and you can actually, configure this in the same prism-based configuration, and you can actually pass counter-propagating waves on this layered structure, what you are going to observe is a very interesting thing. You can see that in this structure, the normalized intensity along the z-axis, that is Ez square, is much larger to the very near distance. You can see that much larger. What it means is that it is going to give a very good penetration in the z-axis, very good enhancement in the z-axis, and we are trying to do that, and we were able to get this data about 25 nanometer with approximately not 8 but approximately 6 aspect ratio. And that is actually the work we have done as far as this interference based approach is concerned. So that is about the periodic structures. I would like to actually break that periodic structure patterning from the semiconductor point of view. Now I would like to give you some stretchable nanostructures. How can we actually pattern stretchable micro nanostructures? And that is what we are going to discuss now. This kind of stretchable nanostructures has got a lot of application on-chip devices, for beam steering and spectroscopy. So what we need to do is that we need to first identify the optimum wavelength, and we have to have the configuration. And I'm going to show you a configuration that is using this femtosecond laser at 343 nanometers. And we were using this configuration to do this patterning. The normal interference patterning, not near field, okay? The normal interference patterning. And you can see that these are 2 femtosecond pulses. And the material that is used is actually a PDMS, an unprocessed PDMS without any manipulation, okay? The raw. And then we were able to get a volume holographic pattern, which means that the thickness of this is actually larger than the wavelength that is going to use there, okay? When you are actually meeting that criteria, you are already going from the Ramannath regime to the Bragg regime, and you are going to get nice Bragg condition there for Bragg refraction, etc. Okay, and that is actually we are going to discuss here. And when you do this, you can actually modulate the refractive index. It is, you might be knowing that when you use UV laser with a photosensitive optical fiber, you can inscribe gratings, that is such as uniform period grating or chirped grating or long period gratings like that for various sensing application. This is something like that, but this is actually in the volume fashion, okay? That is actually, the thickness is larger there, and you can see that the refractive index modulation here is 1.95 into 10 to the power of -4 of that order, and that is going to give you really a volume phase grating, not surface relief type gratings, okay? And such structures, if you pull like this, you can actually stretch it. And you can see that when you do such a stretching, you can actually use it for various applications. You can see that you can control the the theta, the Bragg angle for different wavelength. When you use different wavelength, you can see that you can control the Bragg angle, and the stretching ratio is going to really affect your tunability. And the next slide is actually going to show you that. I would like to emphasize one point before going to show that demonstration of that result, that we need to make sure that the energy density that is supplied there is always under this dotted line. It cannot be anywhere in this region 4 or region 3 or region 1. And it is a very, very important condition. And so there are a lot of theoretical work is also done on that. So based on that, once you identify this region, you need to control the exposure time as well as the fluence that is required for getting such patterning, and you can actually get a very interesting pattern. And you can see that when you stretch it, the strain ratio, you see that when you stretch it, when the strain ratio actually varies, you can see that the theta B is actually going to change. For a single wavelength, you can see that the theta B change is actually going to do the steering job, okay, steering of the beam. In the similar fashion, if you use a supercontinuum laser or a broadband lights, another broadband or semi-broadband light source, you can see that by stretching, this is the percentage stretching. You can see that you are actually getting the different wavelength. So this is surprisingly sorry, the video is not, it's hanging there. I'm sorry for that, but I believe that these two are self-explanatory. So you can actually stretch it and then you can get this application. So the only difference compared to the previous one that we use for the patterning on the silicon wafer is actually here, the surface is actually stretchable, and we use the optimum wavelength based on the principle which I mentioned in the initial slides. Okay, so that is how we can actually do this. The next one is, so we have actually covered this from a bird's eye view point of view, a fixed periodic patterning as well as a tunable periodic patterning. Now we will go to the random periodic patterning. So when random periodic patterning, always we started with this question: how to fabricate a tunable and reproducible random medium in a robust manner. Because at that time, when this research fellow joined me, he was well trained by Professor Vijayan sir, and we were trying to develop some photonic diode work initially, which is he did this work, excellent work in IIT Madras. So we are trying to do whether we can transfer this into a photonic crystal fiber, which is though that work is not what we did eventually. We were actually trying to initially find how can we actually make a random structure. So then we thought that, okay, we were doing a lot of speckle work. Speckle itself is a random structure. Why can't we use that for writing? Okay. So we thought that we will do that. So the randomness then depends on the size, position, and shape. So we use a very simple configuration. This research staff of mine actually, was very much sincere in developing very many different nice apertures. This is actually the major optical element, I would rather say. The aperture size we have actually defined based on certain simulations, and the distance between the D, CL, and aperture size has been actually manipulated, varied, and this is the simple configuration. And you can see that this is a normal laser beam that we used, and then we use this beam expander and the diffuser plate which generate the speckles. And this unit, the distance between D, the lens, the convex lens, and the aperture is going to give you patterns like this. These patterns, very random oriented patterns, which will be printed on this surface. But then we need to actually find some number, how we are going to quantify this randomness, because it's very important in our work. So we had a few, quantifiable numbers such as areal number density, radial distribution, etc. So based on that, we actually classified a few patterns, and based on this variation from this D, CL, and A, etc., as well as aperture, we are using square aperture, elliptical aperture, etc. We are able to make this density varies. The density vary by a large amount. And from S1 to S4, these are the sample pieces where we have actually patterned these features. If you actually put this under microscope, you can see these patterns. These patterns are actually, I will not say that fully random, but it is quasi-random, because in certain direction you can see it is periodic, but overall it is actually random as well. Okay, so such patterns, and depending upon the the intent, the density of the pattern, we were able to make very, very dark silicon. And you can see that the reflectance for such patterns, when imprinted here, the reflectance is actually reduced to less than 10%. What it means is that if you have such a surface, it is going to absorb large amount of light when it falls on top of the surface. So immediately this was tried with a modular unit of solar cell, and we found that the absorption has been enhanced by a large amount, and that is what we have done. We have also varied this pattern, and we made very bright silicon as well. Very bright silicon, mimicking some of the things that you can see in the nature. Okay, the other one, what we have done is we again started changing or designing this aperture in a very special manner. The aperture dimension is changed in such a way that the thickness is reduced to few hundred nanometer. When the thickness was reduced, we found that there is actually a diffraction occurring there, and this is going to create a kind of a pattern, very random oriented diffraction pattern. When you use a single aperture, this is what you are going to get. And if you change this pupil with multiple apertures, with thin, the dimension of this aperture edge is very, very thin, then you are going to get, the 2D gratings. Needless to say, you can see the diffraction pattern that you can get using different light wavelength when you use a one dimension and as well as a two-dimensional grating structures. And this is a very, very interesting pattern, and it has been applied for some of the applications. And this is actually just to show that this is really random, because the pattern dimension is actually varying. But all these are in micro scale. And you can see that this is, if you actually put this structure in between a silicon, two silicon surfaces, you can see here, that is silicon, random grating silicon sandwich structure. And we found that the transmission is actually reduced to a great extent, okay, 30–40%. And that is actually the way we can actually improve the absorption. And this is used for solar energy applications, which is another work we have done, okay. The next one is, I want to use the same configuration. And we are going to do something here, and we are ending up with a very interesting result. The purpose of this work was to mimic the Namib beetle or the desert beetle, mainly to develop some frost control capabilities, or we want to develop some kind of super hydrophobic structures. And what we have done is we actually generated, we made a kind of elongated speckle through that aperture. What actually happening there is, where, you have seen that this structure, you can see that when this is going through this, make sure that this diffuser is actually going to create the speckles. And then you are actually creating a diffraction pattern there. There is another element here. And you can see that these diffraction patterns go through an aperture in such a way, in such a way that the zeroth order is going to be effective in the far field. So what is going to happen is that in the far field, when you are doing the patterning, the speckles are getting elongated. The speckles are going to get elongated in this kind of a shape. It's very very random, and this structure exactly mimic this Namib beetle structure. This is taken from a literature that is published in Nature, and it was mimicking exactly the same structure. Then we found that this kind of structures has got a very good hydrophobic capabilities. And this hydrophobic capabilities, we found that by tuning this DL distance, the distance between this aperture and this lens, we can actually tune this surface in terms of contact angle. It can actually, the contact angle can be changed from 155 degree to 110 degree. Some of the work that we have done, I'm showing here, and you can actually get very nice hydrophobic properties. I'll show you a video of, maybe due to the benefit of time limit, I show one video here. This is actually, there are different areas in a circular fashion. We have patterned those Namib beetle structures, and this is just water droplets. And you can, this just water droplets is what we have done is, it is not only we are controlling the contact angle, we are able to also control its flow. And this controlled flow is later used for controlled liquid circuits applications. And this is the kind of things you can use with interference-based micro and nanoscale writing. I think that is what I want to convey here. I don't want to actually prolong it further to make it a radiation training seminar, and this is lunchtime here, and I hope soon you will be also having lunchtime. So I just want to thank all my students who has contributed to the work so far presented, and their photos are here. This is the colleague Dr. Jaya Bingi. When he was here, he did this random optics. The others actually did this aerospace structures and other all this line biomedical optics. I'm very happy that they all are in multinational companies and in other education institutions. He is in IITDM Kanji somewhere. So they're all doing fine. And the current work that we are doing is actually, I just want to briefly touch upon the current work. This is actually on the diagnostic biomedical optics. Dr. Sandeep is the senior scientist in my group, and he is actually developing new approaches for basal light sheet system for iridio-corneal angle imaging, corneal imaging, etc., for ocular diagnostic imaging applications. And as I told you, I should thank Professor Vijayan sir. I am basically do research with in a straight way, and he actually made me to do some random optics. And we have actually joined together, and we have a joint PhD student, Ms. Gayatri, and we are doing complex cavity lasers for very high resolution called high quality imaging. And this is Professor Balash Gulias and Dr. Padmanabhan, who actually in our team. These are all ongoing work, and there is also another research fellow, and again a collaborative work with IIT Madras, Professor Vijayan sir, and we are doing bio-inspired plasmonic random lasers for very many sensing applications. And the next one is actually a very significant project. The recent research has been published in Nanoletters. It is graphene layered heterostructures and magnetoplasmonics. And of course, my PhD student, Maria, she is developing a hyperspectral imaging system, very custom fabricated, using custom fabricated fiber probes. And this is used for many industrial applications and biomedical applications. And then the next important project is for the Industry 4.0, looking into the next generation aerospace and marine structures engine applications. And that is metrology of shiny surfaces and 3D printed parts, multimodal NDT and E. Dr. Ashwin was my PhD, and he just left and joined Airbus. And then I want to tell that I initially want to talk a little bit about the Industry 4.0, but I understood that there is a big talk coming in this ROWS webinar series, so I skipped from that topic. So I want to tell that the next generation research should seriously consider incorporating AI, big data, and data analytics. And that is one of our research focus as well, using this big data, data analytics, as well as artificial intelligence for various applications. And it is not nice to conclude my presentation because I used a lot of interferometry here. I should thank very many people who actually brought me into this research area. I started my master's in Cochin University, and I was doing a project under Professor Namburi sir, Professor VPN Namburi. I believe he is in this audience. And at that time, I happened to come across, I read a lot of books at that time. I come across this book, A Course of Experiments with the Helium Laser. I'd like to say that I know that Professor Sidhu has written very many books, very excellent books, but this book actually changed my interest. I even quit my job at that time and continue in academics because somehow I got interested in this laser optics research, and I joined for PhD program under him. And after PhD, I started doing a lot of industry research, and this book was actually the book I refer a lot. And incidentally, recently in 2008, I happened to meet both of them together, two legends of this interferometry, optical shop testing, or optical metrology. I cherish that moment here before concluding. And I would like to say that research is always a serious thing. I know that my students also say that it's a very serious activity, but we also enjoy. And this is Gayatri's hobby, and she actually did this, her photographic hobby, while doing experiments. And this is actually a very good guided edge emission from a plasmonic random laser that she was doing. And this she sent to SPIE, and this is one among the selected photos from a huge number of entries. And I congratulate Gayatri for this. We are actually entering into the industry 4.0. I always believe that the technology with the right human interaction is what we have to do, which will make our imperfect world as beautiful as always. With that, I would like to actually conclude this talk, thanking Professor Shankaraman once again for inviting me to deliver this talk. Professor Gopchandran sir and the whole organizing team for putting up such a good webinar series.